Our today topics, maybe from the first 3 weeks, we spend time for the modeling of dynamic system. And we talk about the component of dynamic system and how can we obtain the equation of motion when we have like different connection of the component in the system, both translational application and rotational application. We try to like apply the Newton's second law of motion to obtain equation of motion. And also we talk in detail of the component of vibration system. For example, the spring, the torsion spring, the linear spring that connect in series, in parallel, or in general combination. And also the damper, we talk in the detail, how can we assume the damping force as a constant multiplied by the velocity of the things. So yeah, we already spent 3 weeks for modeling of system. And today is the first class that we're gonna begin the content of vibration. And if you still remember, we talked about degree of freedom. Many times I asked you like how many degree of freedom of the system, and sometimes we have 1 degree of freedom system, sometimes we have like multiple degree of freedom. But for today, when we begin talking about the vibration, we begin from the simple case, single degree of freedom. And of course, we can apply the idea of the vibration analysis to multiple degree of freedom. Maybe after midterm, we may begin to apply the idea of free vibration, damped vibration on multiple degree of freedom system. So the content for today, we're gonna have of course, the introduction to the free vibration and the type of vibration system. And for a single degree of freedom system, when we have spring, when we have mass, and when we have damper in system, this simple system gonna have the equation of motion like depend on if we have the external force apply or not. But it's the second order system. We need to consider until the second time derivative of the coordinate x or coordinate theta depend on your system. So today we're gonna talk about the standard form of second order system. Here is not standard form, but it's the equation of motion that describe the system. The equation of motion that we obtain from the Newton's second laws of motion. So, or the second order system can be modified, can be transformed, or rearrange the form of the equation to be in the standard form. The standard form, when we see the standard form of equation of motion, we can pick out some characteristic of the system easily when we rearrange the equation of motion in the standard form. So today we will introduce the standard form, and we will try to have an example of how can we obtain the solution of the equation of motion. How can we obtain the response of the vibration from the standard form? And of course, we're gonna obtain the response from the equation of motion. And the response here depend on the root of the equation, depend on the root of the equation. So we're gonna classify the possible types of root of the equation. If you still remember, this is the second order equation. So we may need to do something like use the auxiliary parameter R to represent the time derivative like this. And when we solve for the R from the second order system, it's gonna be the quadratic root it's gonna be the quadratic root so if we see here, the second order system gonna have two possible root, depend on the one that we have the plus, the second one gonna be the minus. So we're gonna have R1 and R2, the root. And R1 and R2 can be real number if the things inside the square root is positive. R1 and R2 gonna be the distinct root, real root. If the value inside here, inside the square root becomes 0, we're gonna have the repeated root. R1 and R2 will equal. If the value inside the square root become negative value, we're gonna have a complex conjugate. Real can be distinct or repeat, or can be complex conjugate, depend on the value in the square root. So the different type of the root can be related to the characteristic of the response, whether xt gonna vibrate or just decay or increase the magnitude of vibration. It depends on the root, the value of the root, and the type of the root. So today, we will give you an idea so that in the future, if you see the complex conjugate root, you can forecast what you are going to see in the response. If the root is complex conjugate, have the imaginary part, because here gonna be negative in the square root, you can see vibration. If the root is real number, don't have the complex part, we won't see the vibration. So here is just the introduction, but today we will have the extensive explanation on this. How can we consider the type of the root and can relate to the corresponding response. And Free vibration, free vibration. The meaning of free vibration is the vibration will be under the effect of the initial displacement and initial velocity. We may move the mass to deviate from the equilibrium. When time equal to 0, we may move the mass to the positive from the equilibrium. And after that, it's gonna vibrate as the effect of the initial displacement. Or when time t equal to 0, we may try to add some velocity to the mass so that the initial velocity is not 0. And it's gonna continue vibrating. But the keyword free vibration, it means the force that we apply to the system need to be 0. We don't have external force except the spring force, the damping force in the system. We don't have the external force that apply to the system. External force becomes 0. So in this case, it's free vibration. The vibration only the effect of the initial condition, but no external force. It's gonna be free vibration. And today, the simplest form of free vibration, and you're familiar with this, is we have a spring and a mass. We have a spring and a mass, and we don't have damper. You may be familiar with this from the simple harmonic motion. Have only the mass and the spring. When we have only the mass and the spring, and we begin from the initial condition, the system will continue vibrate forever, never stop vibrating. But we still need to know the period. We still need to know the period, the natural frequency, the magnitude of vibration is still important. So today, we mainly focus on the undamped free vibration. You know why the system can continue vibrating when the time passes? If we consider in the energy term, if the system have the initial displacement, it means you store the energy. In the system. You store the energy in the system. And this potential energy, the elastic potential energy, gonna be transformed to the kinetic energy, depending on where is the position of the mass when the time passes. In another way, if you begin the system in the initial state, when x0, initial position equal to 0, but you add the velocity, when the time equal to 0, you suddenly add the velocity, initial velocity, when x equal to 0, but x dot has the velocity. At that time, your system has the initial energy. Your system has the initial energy from the initial speed, initial velocity. And this kinetic energy gonna be transformed to the potential energy when the spring is under compress or stretch. So although we don't have the external force applied to the system can vibrate by the initial condition in terms of energy. Okay, so today we're gonna talk about the free vibration when force equal to 0. And the simplest type of the free vibration is the undamped free vibration. When we have only the spring and mass in the system, and we don't have the damper that dissipate the energy from the system. When we don't have the damper to dissipate energy from the system will continue vibrate forever, never stop. And next week we're gonna continue when we have effect of the damper. So when we have the damper C in the system, if the damper has a small value, small damping coefficient, the vibration will be like slowly decay the magnitude and stop vibrating, decay the magnitude, and finally stop the vibration. This case is the case of like maybe under damp when C is small. When C is very big, bigger than one value, you are not going to see the vibration. Here we can call x when time t equal to 0. x0 is non-zero. When C is big enough, what we are expect to see is, it seems like you have high damp in the system. You may imagine on like some system that have a high damping in the system. It's not going to vibrate. When x0 is not 0, but your system have a big value of the C, the system gonna move from the initial position by the spring force and come back to the position when spring force becomes 0. Come back to the initial length of the spring. How to say, the free length of the spring when the spring force is 0. But if you compare these two cases, when the damping coefficient is more, you can see the vibration. Vibration means it go over, it cross the 0 line. If you talk about the spring system, and here is the free length of the spring, you move the mass to the right hand side of the equilibrium point, and you also have the damper in the system. If the damp is more, when the mass is on the right hand side of the equilibrium point, if the damp is more, the vibration will begin. The mass will go back and pass through the equilibrium point and reverse, and finally stop by the effect of the damper. But if the damper is big enough, if the damper is big enough, the mass just slowly move and stop at the free length of the spring. So yeah, it depends on the value of the C or the damping coefficient of the damper, but it's the relative value. We cannot only say that, hey, if we have this C, the system will be under damped or over damped. We cannot say like that. Its relative value means you also need to consider the K and the M of the system also. For example, if K is big, the spring force gonna be dominant. Also, although you have small, although you have big damping coefficient, but if you have big K or the stiffness of the spring also, the effect of the spring in the system will dominant, and maybe the system still vibrate, although you have big value of the C. But in some system, if K is very small, but C is big enough, you are not going to see the vibration, and it's gonna be in the overdamped case. So the name of the case come from underdamped, gonna be the damping coefficient is small, and overdamped gonna be the damping coefficient is big enough. The critically damped will be the case when just only one point, when it turns from this to this. Only one value of C will make it be critically damped. Actually, if you come back to the root of the second order equation, the quadratic root, you may can like imagine when we have the complex conjugate, we're gonna see the vibration. It's gonna be in the case of the underdamped, maybe in the distinct root, when in the square root be positive, we may see the case of the overdamped. But when we have the repeated root, when here becomes 0 inside the square root, it's just only one value of C that can make the value inside the square root become 0. So at that point, it may be related to the critically damped. So yep, it's long introduction, but let's see. Maybe this slide maybe slightly repeat what I have already mentioned in the first slide, but let's read the first bullet together. So the free vibration only have initial. The free vibration only have the initial disturbance. When time t equal to 0, initial position, initial velocity, just only one case. Maybe you're gonna have initial position non-zero, but 0 velocity. Or maybe you're gonna have non-zero velocity, but 0 initial position, or the combination of these. both two possible way of this. Zero position, non-zero speed, non-zero position, zero speed, or non-zero position, non-zero speed. These are initial disturbance, but without external excitation means the force zero. This is the free vibration. So again, is the conversion of the potential and kinetic energy without the non-conservative force. So non-conservative force can be the force that we apply to the system. But for free vibration, external force already be zero. So non-conservative force mainly means the force generated by the damper. The force, the work dissipated from the system by damper. So yeah, damping force is non-conservative force. Maybe friction, static, kinetic friction, that like constant and not related to the velocity, or the fluid friction that vary with the speed, or type of friction, the fluid friction or the Coulomb friction is non-conservative force in the system of the free vibration. And the conversion of potential and kinetic already introduced in the previous slide. Kinetic energy in the beginning, maybe, yeah, in the general term, kinetic energy should be 1/2 mx dot t square, depend on the time and depend on the velocity. And the potential energy depend on the position that measure from the free length of the spring. And okay, this bullet also repeat the second bullet. The dry friction, static, kinetic friction between dry surface and the fluid friction and the spring. If we consider in detail, the spring itself may also have the friction in the spring. For linear coil spring, the friction in the spring comes from when the coil in the first and the second coil scratch with each other during it deform. When the coil scratch with each other, we can see the loss. We can have the internal spring friction for the coil spring. When you compress it to be a very short spring, and when it needs to rebound to the original length, if we can have the relative motion between coil and it scratch with each other, at that time we're gonna generate the spring internal friction. And yeah, for the torsion spring, if if you're at home now and you can find the clamp to clamp your shirt, the clamp to clamp your shirt, in that clamp you're gonna see a kind of torsion spring, a torsion spring. The torsion spring, how can I draw the clamp that you need to clamp shirt? It's gonna be something like this, right? Not sure. It have a hinge and you can apply your force to open the clamp, and if you don't apply any force on the clamp, it's gonna be in the closed position, because inside here, if you zoom in here, you have the torsion spring. The torsion spring means you have the arm of the spring and you have the coil of the spring, multiple coil of the spring. And when we compress this and compress this, the spring will deform and the coil of the spring will be under stretching, and by the elastic property of the spring Y, it tries to return to its original length, and it means the spring coil try to reverse to its original posture. So again, the clamp have the torsion spring. The clamp has torsion spring, and the friction between the coil, will dissipate energy. Aerodynamic drag. Aerodynamic drag vary with the low or the density of the air. The frontal area of the moving object. The frontal area means if you see the car from the front view. If you see the car from the front view, the area here, when you see the car from the front view, is the frontal area. The drag coefficient depend on the shape of the car. Although you have the same frontal area, but if the shape of your car is like a sport car or bullet train compared to a van or truck, although you have the same frontal area, but if the shape is different, the drag coefficient will be different. But the aerodynamic drag vary with the square of the velocity. So you're gonna see the significant effect of the aerodynamic drag extremely at high speed, because it have the square with the power of the velocity. So yeah, long introduction here, but we only to give you example of the possible way that we're gonna have non-conservative force in the system, mainly a kind of different way of friction, fluid friction, dry friction, or the aerodynamic drag. And we should come back to the, what it is, homogeneous second order ODE. What does this mean? Homogeneous second order ODE a homogeneous equation, second order ordinary differential equation, written in the terms of time and generalized coordinate. Here, what is the meaning of the first bullet? It's just m x dot dot when x is a function of time plus cx dot plus kx equal to what should be on the right hand side of the equation if we say this is the homogeneous? Any idea? Homogeneous means on the right hand side of the equation will be 0. We are not going to consider the effect of the applied force, but we gonna consider only the effect of the initial condition when time equal to 0. Initial position and initial speed when time equal to 0. But homogeneous means the external force gonna be 0. And they said that x when time equal to 0 may be x0. X dot when time equal to 0 may be a constant, one constant, v0, initial speed. But in the second bullet, what they said is the solution of this type of equation, homogeneous second order, the general form of the solution gonna be one constant multiplied by the exponential, and maybe the second constant multiplied by the second root exponential function. These two exponential functions are linearly independent. Exponential function with different power are linearly independent. If you say function 1 equal to 2x, function 2 equal to maybe 4x, if you can write that f1, or if you can say that f2t equal to 2 f1t, in this case you cannot say it's linearly independent, or maybe, yeah, but in this case, if the exponential function, the two exponential function cannot be written by the combination of the linear multiplication of each other, so it's linearly independent. So the general form of the solution to the ordinary equation with homogeneous type, we're gonna have the exponential function that are linearly independent, and we need to find the coefficient that multiply to these two functions. But if the equation is the second order, we're gonna have two exponential, and we need to derive the value of the two coefficient. These two coefficient, the value can be obtained when we know the given value of the initial condition. Don't worry, today we will know how to obtain C1, C2 when we know X0 and V0 of the vibration. So C1 and C2 are the constant of the integration, and it can be defined from two initial conditions. And C1 and C2, okay, initial condition gonna be the value of the generalized coordinate and its first time derivative at a specified time. So it don't need to be x0. It can be x when time equal to 1 second, and maybe x dot when time equal to 2 seconds. If you can measure this, you also can solve for C1 and C2. That still make this condition become true. But yeah, in our class, yeah, most of the time I see initial condition consider when time equal to 0. The standard form I already introduced, like, hey, if we have the form that we familiar with, when it's homogeneous, ft becomes 0, we may rearrange the equation of motion to be the standard form the standard form is x dot dot plus 2 psi omega n x dot plus omega n square x equal to 0. This equation depends on the value of the parameter m, c, k, the system parameter. But in the standard form, the equation of motion is written in the terms of the system property. Natural frequency. And damping ratio. System property. The initial form of equation of motion is derived in the terms of system parameter. System parameter means what we can measure from the component of the system. We can measure the spring stiffness, the mass. We have the information of the damping coefficient, but the property of the system will give the information of how the system gonna vibrate. Only two important variable that indicate the system property are the natural frequency omega n and the damping ratio. C value can be maybe 2 Newton per meter per sec, right? Force equal to damping ratio multiplied by the velocity, right? So damping ratio is force per velocity. The unit of force is Newton. The unit of velocity, meter per sec. Yeah, most of the time when you select the damper, you may see they write the unit Newton sec per meter. The damping coefficient have the unit, have the dimension, but damping ratio is dimensionless. The value gonna be from 0 to 1. No. Maybe bigger than 1. The value of the damping ratio between 0 to 1 will make the system be under damped when damping ratio between 0 and 1, the system will be under damped. And when damping ratio is equal to 1, damping ratio is more than 1. When damping ratio is equal to 1, it's going to be critical damp. When damping ratio is more than 1, it's going to be over damp. Over damp means the damp is too much. Under damp means the vibration is under the effect of the damper. And please, how to say, be careful between the terms undamped and underdamped. Undamped means you don't have C in the system. You don't have C in the system. Of course, for undamped, damping ratio gonna be 0. For undamped, C is 0. Damping ratio is 0. So yeah, I already introduced you the damping ratio, but you may still cannot get the idea. Hey, if we know MCK, how can we relate MCK to the natural frequency and the damping ratio? Do you have any idea? How can we relate? The natural frequency and the damping ratio to the system parameter? If we consider this term, first, omega n, natural frequency square, need to equal to k per m. So the natural frequency can be obtained from the square root of k per m. You familiar with this from the simple harmonic motion? How about the second terms? 2 psi omega n 2 psi omega n need to equal to C per m, right? It means that the damping ratio can be C per 2 m omega n. But here is simple. If you perform this calculation in numerical, you already obtain omega n. You know the C value, you know the mass value. You can obtain the damping ratio. You can obtain the damping ratio by continuously calculate. But hey, if we want to derive the damping ratio in the terms of the system parameter, how can we do that? We already know the omega n, right? So C per 2 m and the square root m per k, right? The square root m per k. So finally, the damping ratio can be C per 2 square root km. Okay, so until now, if you know the K, C, and M of your system, you can compute the natural frequency by square root K per M. And you can compute the damping ratio by C per square root Km. And what next? Let me check the slide. Solution on complex plane. We may assume the solution. Wait a second. We may assume the solution in the form A e power alpha t. Wait a second. I will come back in 1 minute. Sorry. And let me share the screen. Okay, so before this, what we know is if we know the system parameter MCK, we can derive the natural frequency and derive the damping ratio. And the next step I want to do is how can we obtain the root of the standard form? The root of the standard form will relate to the response of the system. Before this, we mentioned that the response gonna be in the linear combination of the two linearly independent solution. But here, if we try to assume the solution to be in this form, and if the solution can be in this form if true. This equation need to be true. If we assume the solution into this form, and this is the solution of the equation, it needs to satisfy with the equation. So the first term x dot dot, the first term x dot dot. Hey, if the solution is this one, xt equal to a e power alpha t, what is the second time derivative of xt? You may remember that d by dt of e power alpha t will equal to alpha of e power alpha t, right? Alpha, when alpha is constant, and the second time derivative of e power alpha t is alpha of d by dt. No, the second time derivative will be d by dt of the first time derivative. And what we are going to have is we're going to have alpha square of the e power alpha t. So from the standard form, x dot dot plus 2 psi omega n x dot plus omega n square x equal to 0. If we assume the solution to be in this form, x dot dot gonna be a alpha square e power alpha t x dot gonna be a alpha e power alpha t, and x gonna be a e power alpha t, and need to be equal to 0. How can we combine the terms? All the terms has a e power alpha t, right, as the common term. So in the parentheses, if we separate the common, it's gonna be alpha square plus 2 psi omega n alpha plus omega n square of a e power alpha t need to equal to 0. It means that the alpha, we know that this term cannot be 0. A is a constant. E power alpha t, it's impossible to be 0, except maybe when time is very big or very small, but it's just close to 0, but it's not going to be 0. It means that this one needs to be 0 so that this solution can be true. But it's not a big deal. This one is if you want to make this one to be 0, it's not difficult, right? It's just the second order equation, and we need to obtain the quadratic root of this. Let me repeat this one in the next page. Alpha square plus 2 psi omega n alpha and omega n square need to be 0. So if this is 0, it means the alpha can be obtained from the quadratic root. Quadratic root means, if you still remember, when we have a x squared plus bx plus c equal to 0, the quadratic root is x equal to minus b plus or minus b squared minus 4ac minus 2a, the quadratic root. I hope you still remember. So alpha need to be minus b plus minus square root b square 4 sine square omega n square. 4ac means the coefficient in the first term is equal to 1, right? And finally divide by 2a. So here the alpha gonna be minus sine omega n plus minus square root I gonna make okay, it can be like psi square omega n square subtract by omega n, right? Okay, omega n square subtract by omega n square. But I don't like this term. Because we know that mainly the damping ratio is between 0 and 1. So if the damping ratio mainly between 0 and 1, if we just leave it in this form, the value inside the square root mostly is going to be less than 0. So another useful term is to prepare this root to be in the form of the complex j or I, and bring the omega n outside, and inside gonna be only 1 subtract by the damping ratio square. So I switch the order of the term and have the imaginary j, and omega n square, bring it out from the square root, it's gonna be omega n. And we name this one as omega d, or damp natural frequency. We have natural frequency omega n, but if we consider the effect of the damping ratio, it's gonna be the natural frequency that already damped by the effect of the damper, and we use omega d to represent the damped natural frequency. Do you think in general omega d is bigger or smaller than omega n in general? In general, do you think omega d is bigger or smaller than omega n? We need volunteer. So no volunteer. So I may need to pick.
I think omega n, sir. I don't really know.
Okay, so we now we know that omega d is equal to omega n multiplied by square root of this one. Do you think this term should be more than 1 or smaller than 1?
Lesser than 1.
So when it multiply to omega n, so yeah, most of the time omega d will less than omega n. You need to imagine if you have one system and we have only the spring and the mass in that system, and you make it vibrate, it gonna vibrate with one frequency. If you have only spring and mass and you make it vibrate, it gonna vibrate with omega n equal to square root k per m. If you add the damper to the system, do you think the damper gonna make the system move faster or slower than the original frequency? Just answer by your engineering sense. If you add damper that always resists the motion to the original system, do you think the frequency of vibration will increase or decrease from the original system?
Decrease.
Yes, you make the system vibrate slower. So this is the answer. Omega d always less than the omega n. The damp natural frequency, when we add the damper, if the original system have omega n as natural frequency, when we add them to the system, it will decrease the natural frequency. Yeah. And okay, I need to introduce you an S-plane. It means now we have alpha equal to this. Alpha equal to minus sine omega n plus minus j omega d. It's a complex thing. I'm going to introduce you this one. I should make it bigger. We have the imaginary part of alpha, and we have the real part of alpha. The real part of alpha gonna be minus sine omega n. The imaginary part of alpha can be plus and minus with the magnitude omega d. In the axis j, imaginary axis. And if you come back to the definition of omega d is equal to omega n multiplied by square root 1 subtract by the damping ratio square. So square root 1 subtract by damping ratio square multiplied by omega n. If we have the angle phi, if we define an angle phi here, we have one triangle. This triangle. This side of the triangle have the magnitude psi omega n. The vertical length here is equal to omega n multiplied by 1 minus psi square. What should be the length here by Pythagoras? What should be the length here? The horizontal length.
1.
Yes, but 1. Don't forget to multiply by omega n. Right? By Pythagoras, this side should be the square root of this one square. And this one square. And yeah, we're gonna have omega n and the square root of psi square plus 1 minus psi square. So yeah, the magnitude of the length of this side gonna be omega n. What I'm going to introduce here is when we have the root alpha, alpha will have the component in the real part and the component in the complex conjugate, and we mainly talk about the damping ratio phi, no, the psi, damping ratio psi, and we introduce an angle phi to here, but this angle cos of phi is equal to psi omega n divided by omega n. This angle is directly related to the damping ratio. Cos of this angle psi is equal to the phi. No, cos of phi equal to the psi. Why I'm trying to draw this picture to represent the alpha. We redraw the picture again. We have imaginary part of alpha and real part of alpha. This picture is very important, but if maybe here should be better, but I'm gonna redraw this one, and we only want to keep this one, the form of an alpha. Alpha is equal to minus sine omega n plus and minus j omega n square root 1 subtract by sine square. And this one is the damped natural frequency. And I redraw the picture when we have the imaginary part of alpha and when we have the real part of alpha. If alpha has in the case one undamped free vibration, with free vibration. For undamped free vibration, what is the value of the damping ratio?
0.
Yes, undamped free vibration means we don't have C, right? Undamped, not underdamped. Undamped when C is equal to 0. When C is equal to 0, if we come back to here, damping ratio is C per 2 root km, right? Damping ratio C 2 root km. If C is 0, damping ratio gonna be 0. When damping ratio is 0, do you think what we gonna get from alpha? When phi is 0, the first term, the real part gonna be 0, right? The real part gonna be 0. The complex conjugate gonna be J. And damping ratio 0. So we only have omega n. It means that in case 1, if we plot it on the complex plane, the real part gonna be 0, but we have the complex conjugate plus J omega n or minus J omega n. In this type of the root, when we only have the complex conjugate and the real part becomes 0, the vibration of this will be like a simple harmonic. It will vibrate with a constant magnitude and vibrate forever. Sorry. Wow. Can you see if it full screen or it have some dark shade on the screen now? Or on the screen?
Full screen, sir, no dark shade.
Okay, thank you. Simple harmonic motion. So in the first case, for the undamped without the damper in the system, damping ratio will be 0. And the root gonna be only a complex conjugate when the real part is 0. And we're gonna see the simple harmonic vibration. The second case for the underdamped vibration, the damping ratio will be between 0 and 1. When the damping ratio between 0 and 1, of course, we can see the minus sine omega n and plus minus j omega d. So when we plot the root of the second type on the S-plane, we're gonna see minus psi omega n, and the complex conjugate the root of this type have the real part on the left hand side of the imaginary axis and also has the complex conjugate. The vibration that correspond to this type gonna be the vibration with big magnitude that decay the magnitude and stop vibration. And in the critically damped, for the critically damped, when the damping ratio completely equal to 1, alpha, when the damping ratio equal to 1, the imaginary part gonna be 0. Imaginary part gonna be 0. And we're gonna have only the real part, If alpha don't have imaginary part, but alpha has only real part, if alpha don't have imaginary part, but it is on the real axis, it have only the real part, we are not going to see vibration. But the magnitude gonna decay from the initial value to the 0. It's gonna decay. If over damping ratio is more than 1, alpha gonna be minus psi omega n, and if the damping ratio is more than 1, we are not going to see the complex conjugate, but we will see omega n multiplied by square root of the damping ratio subtract by 1. For the overdamped case, we're gonna have two real root. Because this one will be positive things. And the positive one will be plus to this negative and will be minus to this negative. But what we are going to see is we will see two real root on the real axis. We're gonna see two real root on the real axis. What I'm going to say is every time when we can see the complex conjugate, we will see the vibration. This will vibrate. And the complex conjugate tell us whether the system gonna vibrate or not. How important is the real value? If the real value is 0, it's gonna vibrate forever and not stop vibrating. If the real value is negative, the vibration decrease its magnitude and stop vibrating. If the real value has the negative value, it's gonna stop vibrating or stop motion. We call this stable. Stable means it stopped moving. But in some unlucky case, when we have the, how to say, for free vibration, we are not going to see the real part in the positive region. But in some system, when we have additional excitation or force, we can see when the real part become positive. When the real part become positive and it on the real axis, it simply increase the magnitude with our vibration. Simply increase the magnitude with our vibration. But if we see complex conjugate, when we see conjugate, of course, it's gonna vibrate. But if the real part is positive, the vibration will be increase the magnitude, bigger, and unstable. So how about here? If we see some zero root, what do you expect to see from this? The zero, completely zero, have no complex conjugate, so it's not vibrate. And it's not on the left or on the right of the real plane. So the magnitude doesn't change. So for the zero, what you're going to see is the magnitude will be constant, not vibrate, and doesn't change the magnitude. I think here is the introduction to the complex plane. If you see the root of your standard form equation of motion, and you consider the natural frequency, consider the damn natural frequency, like try to check if we only have the complex. The first thing we need to check is, do we have complex conjugate? Do we have complex conjugate? If we have complex conjugate, J, the system vibrate. The second thing you need to see is minus sine omega n. If it's negative, the system stable, means it decreased the magnitude. If sine omega n is minus sine omega n sometimes positive, the system is unstable and it increased the magnitude. Just only this. You have to point to check if it have the complex conjugate J or not, and check if the value of minus sine omega n is on the left hand side or the right hand side of the S plane. Okay. The root of second order. Okay, so maybe this one will be the review from the ODE, the differential equation class. If we have a simple equation with a constant multiplied by d square x by dt square plus a2 dx by dt and a3 x, and for free vibration, maybe homogeneous equation just equal to 0. So in this slide, we are going to just obtain the root of this. I'm not sure if you want to have like 5-minute break before we continue, but we should. So let's break for 5 minutes and please come back by 2:40. Let's have a break for 5 minutes. I already continue recording, and let's continue. Okay, maybe for this slide, we are going to review the deep equation class. We are going to solve this differential equation by using the auxiliary parameter. Transform from the differential equation to the a1 r squared plus a2 r and a3 with the 0 time derivative equal to 0. And of course, we need to solve for r1 and r2, which are the root of the equation. We are going to obtain r1 and r2 by minus a2 plus minus square root a2 square minus 4a1 a3 divided by 2a1, right? And the first possible case that we're gonna have, is the root of the auxiliary equation are the real root. R1 and R2 are the real root, and R1 is not equal to R2. So in this case, if we obtain R1 and R2, and R1 and R2 are the real root that are different, the response of the equation, gonna be one constant multiplied by exponential of r1t plus by the second constant multiply e power r2t. The second possible case is r1 equal to r2. R1 gonna equal to R2 when this becomes 0. If this becomes 0, R1 will equal to R2. If R1 equal to R2, the root will give the response to be the form C1 plus C2 t and e power rt. R1 and R2 are the same and equal to r, right? So for the repeated root, we still have two constants. The second constant will multiply by t, and we have e power rt. For the third possible case, it may be the common one in our class. We are going to see a complex conjugate. R1 equal to a plus bi, and R2 a minus bi as a complex conjugate. In this case, we still have C1 e power R1 t and C2 e power r2 t. But maybe this is not so easy to expect what is going to have for the response when we see it in the complex conjugate. So we're gonna apply the Euler identity. To simplify this type of solution, maybe, okay, let's bring this to the next page. When we have the complex conjugate, complex conjugate is not suitable for describing the vibration system. Of course, theoretically, we firstly derive the response in the form of the complex conjugate, but we need to find the equivalent answer that only show the real value, because in the vibration application, we not only want to describe the system by mathematics, but also we need to measure to confirm the physical meaning, physical phenomena. So of course, from theory, the first thing we obtain is the complex conjugate form, but we need to find the equivalent form that we can measure the real system and compare to the theoretical value. So from this x equal to the first coefficient multiplied by e power the first complex conjugate, the positive one, and C2 e power a minus bi. I think I forget the time. Okay, t. How can we transform this by use the Euler identity? The common term, it seems like both the first and the second term have the e power at as a common term. And we have C1 e power I bt, right? And the second term C2 e power minus I bt. By the Euler identity, we're gonna have e power at and C1 multiplied by cosine bt plus j sine bt, and C2 will be cosine of minus bt and j sine of minus bt. And maybe for the cosine bt, we have C1 plus C2 and cosine bt. And for the second part, when we have J, it seems like sine of minus bt will become minus J sine bt. So the second term may be C1 minus C2 multiplied by J of sine bt. Maybe this one gonna be one constant A. Maybe A1. This one is a complex value, but maybe a constant A2. So can we if we have one triangle, and we have A1, A2, and by the Pythagoras, we will have the A1 square plus A2 square. I am trying to what about I multiply this by A1 square plus A2 square, and I divide by A1 plus A2, and still keep the cosine. And for the second term, we still have A2, and it needs to divide by the square root of A1 plus A2 and have the sine. So this one is a constant A. It's a constant A. Just a constant A. Because it seems like we have the numerical value from the original coefficient. And this one, if you see this triangle, it seems like we have sine of the angle phi multiplied by cosine bt. And we have cosine of angle phi multiplied by sine bt. We have the sum of angle in the sine function. Sine A plus B equal to sine A cosine B plus cosine A sine B. So here we have sine A cosine B cosine A sine B. So we have BT plus phi. This is just a proof that if we have the solution for the response for the case of complex conjugate. For the case of complex conjugate, you may describe your response xt by these complicated terms, or we know that it's equivalent to another simplified form. For the first form here, for the first form here, our task is to give the information of x0 and x dot 0 and derive C1 and C2 and derive C1 and C2. For the second simplified form here, our task is similar. We know x0 and x dot 0, and we need to derive the constant a and phi. We need to derive the constant a and phi. How about b here? B maybe can be obtained from in general, the B is directly related to the complex conjugate. Most of the time, B will be the omega D or the damped natural frequency. So maybe until now, it's still described in the general form of the differential equation. It's not directly related to the vibration problem. Maybe you still cannot imagine, but in our next example, we will show you if we have the vibration system and have the initial condition, how can we obtain A and the phi as a constant and derive the vibration frequency B. But before we move from this slide, the angle phi here is equal to the arctan of A1 per A2, arctan of A1 per A2, and A1, A2, yeah. And also the A here is this one, the complicated term here. But we don't need to know this. We just know that when the root is complex conjugate, the response need to be in this form: A psi omega d t plus phi. And the next step is, hey, how can we obtain A? How can we obtain phi? And we already know what is omega d. So the goal of today's class is to teach you to obtain A, phi, and omega d. Okay, undamped free vibration. Like simple harmonic. We have the spring, we have mass and frictionless. And the coordinate x. Equation of motion for the spring mass damper system. Equation of motion mx dot dot plus cx dot plus kx equal to f. But for undamped free vibration, f 0, c 0, mx dot dot plus kx equal to 0. Auxiliary equation m r square plus k equal to 0. The root of auxiliary equation R1 and R2 equal to R1 and R2 equal to minus k per m, right? Minus k per m, and square root of minus k per m, and the square root can be plus and minus, and it means we're gonna have plus and minus j of the square root k per m. If we come back to the concept of the S-plane, if we come back to the complex of the S-plane, when we have the real value and we have the imaginary, do you think if the root is a complex conjugate without the real value, have only the imaginary value, can you expect what is the expect vibration from this solution? Do you have any idea? The first I want you to check, hey, do we have complex conjugate? If we have complex conjugate, it vibrates. The second bullet is, if we have the real part, if the real part negative, the system stable, magnitude gonna decrease. If the real part 0, magnitude doesn't change. If the real part positive, system unstable. Now, the case that we see, we only see the complex conjugate and the vibration. Magnitude doesn't change, but can see vibration. So it's a kind of simple harmonic. We will see the simple harmonic motion with a constant magnitude. And the response need to be the first coefficient multiplied by e power r1t plus c2 e power r2t. So it may be c1 e power j root k per m t c2 j minus root k per m t. If we apply the Euler identity, e power j omega t equal to cosine omega t plus j sine omega t. Maybe I'm not going to like directly relate c to some constant here, but this form of solution, the first form of solution, is equivalent to a1 cosine root k per mt plus a2 sine root k per m t. It is equivalent to, and also these two form from this concept, the most simplified form is xt will be one constant multiplied by psi of square root k per m t, but have the phase angle, Our task, when we already confirm the type of the root to be this type, when we already confirm complex conjugate with zero real part, when we already confirm the complex conjugate with zero real part, I recommend we use this form. We have one magnitude that is still unknown. We have one phase shift that is still unknown, but the omega of vibration will be the natural frequency, omega n. And by the initial condition, given in the problem, we can solve for the magnitude and the phase shift. Before we check how to solve for the magnitude and phase shift, let's review the simple harmonic. Let's review the simple harmonic. First, we have the vibration of the simple harmonic. Time and the response. And we come back to this type of the solution. We have x equal to 1 magnitude multiplied by psi of the omega t plus the phase shift. And for the undamped free vibration, omega is simply the natural frequency. Omega is simply the natural frequency. How can we relate this to the plot of the response? I think you may familiar with the, if we know the omega and we need to plot this one, the period of vibration is equal to 2 pi per omega, right? And yeah, omega is square root k per m. How about the angle phi? How can we relate the angle phi to this picture? This is a sine wave, and have the phase shift. In the terms of the phase shift, maybe it's not easy, but if we consider the time shift, the original sine plot is shift to the left hand side of the time axis. This original form, maybe if you want to consider the phase shift, you may rewrite it like sine of omega t plus time shift So like this, the meaning of time shift, the meaning of time shift is in this picture, is in this picture. The meaning of time shift is in this picture. The original x equal to a sine x equal to a sine omega t, original sine wave, sine function. This one, x equal to a sine omega t minus t0. No, plus t0. Again, x equal to a sine omega. Wait a second. สวัสดีครับ ครับ let me share the screen. Okay. The sine function with time shift, the sine function with time shift when time t is equal to 0, when time t is equal to 0, what is the value of this function? Equal to 0, right? When time t is equal to 0. When time t is equal to 0, xt, when time t is equal to 0, x equal to 0, because sine 0 equal to 0. No, sorry. When time t is equal to 0, x equal to 0. How about this function? This function has t plus t0. When time t is equal to minus t0. When time t is equal to minus t0 means this distance when to the left hand side, when time t is equal to minus t0 at this time point, x equal to a sine omega minus t0 plus t0 equal to 0. So this is the simple way to check the time shift, whether you have the correct understanding. Like if we shift the plot to the left hand side with the magnitude of time shift t0, to the left hand side, we're gonna see the positive here. But if we shift it to the right hand side, we're gonna see the negative side. So just the review for the time shift for the simple harmonics. So here a sine omega t plus omega t0. So the phase shift, if we see the plot, this is the phase shift, the relationship to the phase shift. The phase shift is equal to omega t0, or maybe 2 pi per t of t0. And the time t0, if we know the phase shift from the plot, if we know the phase shift from the equation, if we need to plot on the if we need to plot the curve when we see the phi, we may try to write the T0 equal to phi per omega or equal to multiply by the period divided by 2 pi. Okay, so here is just the review for the simple harmonic, but I think this is the last slide for today. The last slide for today is we already introduced that the response for the undamped free vibration gonna be in the form A sine omega t plus phi. But if we know that the initial condition is one constant given by the problem, the initial velocity and initial position given by the problem, how can we obtain A and phi from the given IC initial condition? How can we obtain A and phi? So from the original response here, it should correspond to the IC. It should correspond to the IC, both the position and the velocity. If the position response is this one, the velocity response should equal to the first time derivative. Xt is A sine omega nt plus phi. X dot t will be dip sine will be cosine. And dip omega t by dt. We have only omega here. Dip omega t by dt. Dip constant will be 0, so we don't care. So yeah, the first time derivative of the response will be this one. So 1 and 2 need to satisfy the initial condition. Let's begin from x0. X0, it means when time t equal to 0. I should say x when time t equal to 0 from the first equation. X when time t equal to 0 will be A sine phi, and A sine phi need to equal to x0. You already can compose sine phi equal to x0 per A. Leave it here. How about from equation 2? How about the x dot when time t equal to 0? X dot when time t equal to 0 will be omega n A cosine phi. And this need to equal to the initial velocity. So the cosine of phi is V per omega n per A. V per omega n per A. So we have triangle with the phi angle, and sine of phi angle x0 per A. Cosine of phi angle will be V0 per omega n. So A from Pythagoras, A is equal to the square root x0 square plus V0 per omega n square, or maybe simplify by move the omega n outside the square root, move the omega n outside the square root, so we have omega n x0 square plus V0 square. How about the phi angle? Phi angle also the arctan. Arctan of x0 divided by V0 by omega n. So come back to the original form. So xt, A is this complicated things. 1 per omega n, the square root omega n x0 square plus V0 square, and sine omega nt plus phi. Phi is this arctan. So this slide give a hint for you. If we know the initial condition, this is the step. How can we obtain the unknown A coefficient and the phase shift phi? The phase shift phi. You need to know omega n by maybe the square root k per m from your system. But to obtain unknown A and phi, we need the initial condition. We need the initial condition x and x dot. Maybe in the exam, if we have this type of problem, maybe it may be in the numeric form, and you just compute the value of A of phi if it is in the numeric form. So you don't need to remember this. You can derive it if you understand this slide. So maybe we have extensive explanation on this, but if we have one problem for the exam in this chapter, it will be from this slide. But for the simple harmonic, you review by yourself for the simple harmonic. How can we transform the equation to the plot? Maybe I may ask you to plot the response from your answer. So you need to know how to relate the plot to the response. And the S-plane here may be complicated, and it may not, how to say, of course you will use it in the next year control class for checking the value of the root on the complex plane, but it helps you a lot to identify the system just only from seeing the type of the root. So please review about the complex plane here. I think that's all for today. think that's all for today. So if you have any problem about today's class and the record for the previous week, just like ask me in the message or in the email. โอเคขอบคุณครับ
ขอบคุณครับ
ขอบคุณครับ
สวัสดีครับ